A single flipped bit in a computer's memory, 1 0 turned to a 1, was enough to hijack an AI agent and make it call the wrong tools entirely. Here's how that works and why it matters. Welcome to AI Research Chat, your daily briefing on the latest in artificial intelligence research. I'm your host, and joining me, as always, is our resident AI expert. Today is March 12th, 2026, and today we have a great lineup of papers to get through.
Great to be here. Let's dive right in.
Today we're diving into 3 research papers covering some genuinely unsettling corners of AI security. Let's get into the first one. Researchers figured out how to attack an AI agent by physically corrupting its memory, not through the software but through the actual hardware. Can you walk us through what that means?
Sure. So when an AI model is running on a server, all those billions of parameters, the numbers that define how the model thinks, those are sitting in RAM. And RAM is not perfectly stable. There's a well-known hardware attack called row hammer, where you can repeatedly access rows of memory in a way that causes adjacent bits to flip. A 1 becomes a 0 or vice versa. Researchers have known about this for regular software, but this paper is the first to ask, what happens when you do this to an AI agent?
And an AI agent is different from a regular AI model, right? It's not just answering questions.
Exactly. An agent doesn't just produce text, it decides which tools to call, in what order, when to retrieve information from memory, when to stop. It's more like a decision-making pipeline than a single answer generator. So when the researchers targeted an agent with their framework, which they called flip agent, they weren't just corrupting the final output, they were corrupting the decision logic that controls the whole pipeline.
So what can actually go wrong in practice?
Imagine an AI agent that's managing a company's IT infrastructure. It decides whether to restart servers, query databases, send alerts. If an attacker with physical or close physical access to the hardware, think a data center employee or someone who's compromised the facility, can flip just a handful of bits in the model's weights, they can cause the agent to call the wrong tools, exfiltrate data to the wrong endpoint, or simply produce plausible-looking wrong outputs that no one questions.
And the scary part is that software security doesn't catch this.
Right, that's the key insight. Firewalls, input sanitization, safety filters, all of that is running on top of the model. If the model itself has been corrupted at the hardware level, the software never even sees the attack. The model just quietly misbehaves. The paper's recommendation is fairly practical, though. Checksum your model weights before each deployment. Use error-correcting memory in high-security systems. These are known techniques. They just haven't been applied to AI deployments yet.
It's almost like verifying the integrity of software you're installing, but for model weights.
Exactly that analogy. You wouldn't deploy code on a production server without verifying the hash. People are deploying models without doing the equivalent check, and this paper shows concretely why that's a risk.
The next paper takes things in a completely different direction. It's about the military, and the finding that some AI models refuse to answer military questions at a rate of nearly 98%. That number feels almost unbelievable.
It is striking. So the background here is that commercial AI models are trained to be safe for a general audience, and general audience means the safety training errs toward refusing anything that sounds like it involves violence, weapons, or tactical operations. That makes sense for a consumer chatbot, but the same model deployed in a military logistics tool or a training simulator becomes essentially useless if it refuses nearly every relevant query.
What kind of questions are we talking about that get refused?
Think about the kinds of things military personnel legitimately need to reason about. Rules of engagement, weapons maintenance, tactical decision-making under fire, casualty triage protocols. A soldier in a training context asking, what's the effective range of this weapon system? Or how do we coordinate a flanking maneuver? A consumer AI model trained to avoid anything weapons adjacent will just refuse or give a vague non-answer.
So the researchers built a benchmark to measure this. How did they do it?
They worked with U.S. Army veterans and special forces to create a data set of genuinely legitimate military queries, questions that any military professional would recognize as normal and necessary. They tested 31 public models and 3 military-specific models. The worst performers had hard refusal rates of 98.2%, meaning they refused nearly everything. Even the better performers had significant deflection, where they'd technically respond, but in a way that avoided the actual question.
And then they tried to fix this using something called obliteration. That's a great word. What is it?
So obliteration is a technique where you look inside the model's internal representations, its hidden states, and you find the directions in that high-dimensional space that correspond to the safety refusal behavior. Then you literally subtract those directions out. It's like finding the part of the model's brain that's responsible for saying no and removing it.
Does it work?
Dramatically. Applied to a military-tuned model, they increased the answer rate by 66.5 percentage points. The cost was about a 2% relative drop on other military tasks, which for their target use case, they considered an acceptable trade-off. The paper is careful to argue this is appropriate specifically for purpose-built military systems, not for general deployment.
It does raise interesting questions about whose definition of safety applies when.
That's exactly the tension they're pointing at. The same safety behavior that's protective in a consumer context becomes a liability in a professional context where the questions are legitimate. Their conclusion is that consumer models shouldn't be patched for military use. Purpose-built models need specialized training from the start to understand the appropriate scope of caution.
The third paper we're covering today looks at something called guardrail degradation. Basically, what happens to an AI's safety behaviors when someone keeps pushing at them over multiple conversation turns. What did they find?
This one has a counterintuitive result that I think will surprise people. The conventional assumption about jailbreaking AI models, getting them to say things they're trained not to say, is that it's a gradual process. You warm the model up, slowly escalate, build context over multiple turns until the guardrails erode. What this paper found is that the most successful jailbreaks actually happen very early in conversations, with an average successful jailbreak round of 1.25, meaning round 1 or 2, not after a long buildup.
So the sustained multi-turn pressure strategy doesn't actually work that well?
It appears not, or at least not as well as simply getting the first prompt right. And this matters because a lot of safety evaluation has been designed around the assumption that models degrade under sustained pressure. If the real vulnerability is concentrated in those first turns, you need to be much better at catching attempts at round 1, not just monitoring for slow degradation.
How did they actually run these experiments?
They built a custom red teaming system with an attacker model, a fine-tuned version of Llama, 70 billion parameters, specifically designed to attack other AI systems. One interesting methodological point is that they had to fine-tune the attacker to remove its own safety refusals. An off-the-shelf model used as an attacker keeps second-guessing itself and refusing to send attack prompts, which makes the attack inconsistent and hard to measure.
They also tested against some specific models, including Claude Opus 4.6. How did things look overall?
The 26.7% jailbreak rate across 3 frontier models, Claude Opus 4.6, Gemini 3.1 Pro, and GPT 5.2, is the headline number, but the paper is careful about what that means. They used a consensus scoring system with 3 separate judge models, and they measured judge reliability itself as a research outcome, because inconsistent judges are a major confound in this kind of work. They also documented something they call attacker drift, where the fine-tuned attacker model performs well on its training distribution, but degrades when the conversation goes in unexpected directions. That's a new failure mode that hadn't been documented before.
So even the attack tools have their own reliability problems.
Exactly. And that's actually important for the field. If you're trying to measure how safe a model is, and your measurement tool is unreliable, your safety numbers are unreliable too. Part of what this paper is doing is raising the bar for how rigorous adversarial evaluations need to be.
Stepping back across all 3 papers today, there's kind of a theme here, isn't there?
I think the theme is that AI security has a lot of blind spots that people haven't been looking at carefully. Hardware-level attacks on model weights, no one was thinking about that for agents.
safety behaviors that are simultaneously too restrictive and not restrictive enough depending on context, evaluation methodology for adversarial testing that has its own hidden weaknesses. The field is maturing past the naive assumption that safety is just a software problem you solve once.
And the practical upshot for organizations deploying AI systems?
Verify your model weights aren't corrupted before deployment. Think very carefully about whether a general-purpose model's safety calibration is actually appropriate for your use case. It might be both too cautious and not cautious enough in the wrong places. And if you're evaluating AI safety, make sure your evaluation methodology is as rigorous as the thing you're trying to measure. That third point is more subtle, but maybe the most important. You can't improve what you can't reliably measure.
Fantastic. Thanks so much for breaking all of this down. These are some dense papers, but the implications really are significant for anyone building or deploying AI systems right now.
Happy to be here. Good stuff to dig into.